Okay, let's do equality of vectors. Now, this little definition is going to seem like Captain Obvious, and you'll probably overlook it and go, oh yeah, it makes sense, boring. But it's going to come and save us on multiple occasions. So I'm going to put stars by it because it's going to come to the rescue in 2 problems in this lecture. And if I don't finish today, for sure by Wednesday, okay? So, and I'll let you know when it's coming to save us. Don't worry. I'll go to the rescue. Equality of vectors. Yay. So what does it say? It says a vector u that has the component form u1, u2, and another vector v with components v1, v2 are considered equal if and only if their scalar components match. So the u1 had better be equal to the v1. Okay. And the U2 had better be equal to the V2. Okay, and they're equal. Now, again, this seems like, well, of course. I mean, if you had a vector U with components 2, -1, and you had another vector V with components 2, -1, I hope you can agree that the scalar components match, so these vectors are equal. Of course. So that's why I say it seems really obvious. So how is that helpful? Don't worry, it's going to rescue us later. Let's do some vector operations. In other words, adding 2 vectors together, as well as something called scalar multiplication. What the heck? Fill in these blanks. And it's what you would expect too, folks. It's what you would expect. There's nothing mysterious about this definition that you will see. So here we go. Let's have a couple of vectors, u and v. And they're going to be vectors in the plane. What does that mean again?
2D.
2D, good. 2D, yeah. And let's see be some scalar. What's a scalar? Just some pure real number like 17 or 4.2 or -57. I don't know, whatever. It's a scalar. Let's say you were trying to add u and v together. And you already have their component form, which means they're automatically in standard position because you have the component form. And somebody says, hey, can you add u and v together, please? And you're like, yeah, sure. So you're going to take the component form for the u vector and then plus the component form for the v vector. And what the heck is the result? Well, I do claim the result is a vector. So you are going to want to use the angular brackets. So you're going to go bracket, bracket, leave some room in there. And you're going to have 2 scalars separated by a comma, okay? The first scalar is going to be the sum of what I call the x components of your vectors. So the u1 is the x component for the u vector, and the v1 is the x component for the v vector. Just add them together. And then comma, u2 plus v2, and we're done. It's that simple to add 2 vectors together when you have standard position, component form. Okay, what about a scalar multiple of a vector? So what if somebody gives you the vector v, but they want you to multiply it by some number c, which could be positive or negative. So the intermediate step will be you'll have the c sort of sitting outside the vector, fine. Then what? You can think of distributing the c and making it hit each of the components inside your vector, and you're done. And so the scalar multiple of a vector is still a vector. What about the opposite of a vector, which is also known as the negative of a vector? What's that? Who cares? Well, you do, because a lot of times you want to go in the opposite direction of a vector. And it's really easy to get there. You just turn 180 degrees and you put a negative sign in front of it. So negative v, which is the opposite of this component form, and negative is just the same as the scalar -1. So you just distribute it. And so the new components are simply opposite in sign. Easy peasy. What if somebody wants you to subtract 2 vectors? And remember, with subtraction, with real numbers, order matters. And it does also with vectors. So if you were going to do u minus v, That's going to give you a different result than v minus u, so be careful. But u minus v, what is it? There's u minus v. You're going to get a vector, so do your angular brackets, and then you're going to go u1 minus v1, comma, u2 minus v2, and we're done. Now, there's one student who mentioned that they are in linear algebra right now, or if you've taken linear algebra already and you didn't answer my question, I want to say something about the textbook we use here at Southwestern and some issues. In the linear algebra text, Math 254, they don't denote their vectors with angular brackets. They use parentheses instead. And I'm not going to allow that in this class. Why not if the linear algebra folks are doing it? Because it's confusing. Well, why is it confusing? Because in this class, the parentheses are going to be used to represent points. So like if somebody wanted the point 2, 3, so let me just, find the point 2, 3 right here. The point 2, 3 is denoted with parentheses with the ordered pair. Okay? And that's very different from a vector. So the vector with components 2, 3, that would be in standard position, it would look like this. We'll call this vector v. You would use angular brackets with the 2, 3. That's very different from just a dot, a point. And so I am very much a stickler for sticking to that representation in our class. Component form for vector uses the angular brackets so that we don't get confused with vectors and points. Because, and it's going to matter on your quizzes too. If you meant to say a point and you didn't use the parentheses, you started using brackets where it was points or vice versa, I'm sorry, but I'm going to have to take a point off every time you're not being true to what it is. Okay? It's not that hard to learn. Okay, now let's look at some geometric perspectives of vector addition as well as subtraction and scalar multiplication. When I ask you to add two vectors, typically I'm not going to have you graph them very often, once in a while. But if you're in physics, you really have to know visually what these look like because they use a lot of vectors. So take a look. When you do vector addition, there's two ways you can think of it, and both are fine. It just depends on what's the more common way to think about it. And I'll tell you which one of these methods is the more common way in a moment, but not yet. So suppose you had a vector u that was over here. There he is. And say you had some other vector v over here, hanging out in space way over there. And somebody said, hey, I want you to add those two vectors together. So what you're going to do is you're going to translate one of the vectors. And remember, we're going to translate v, which means move them around. Remember that once you have a vector, it represents infinity vectors, as long as you maintain the integrity of it. You maintain the direction and the length. So I'm just going to copy u down again. He's still kind of lying flat on the ground. V, I'm going to translate him so that his tail is on the tip of u. So here's v. We just moved him so that his initial point is right on top of the terminal point of u. That's called the tail to tip method. Well, then what? Well, the vector u plus v is the vector connecting the tail of u to the tip of v. That's this vector right here, u plus v. And that's called the tail to tip method. And there's a picture of what u plus v looks like. All right, let's do the same u plus v. So here's the same u right here. Oops, I can't draw a straight line this morning. U. And let's say v is still over here. Okay, fine. Add those two guys together again. Well, I'm going to translate v again, but in a different way. I'm going to copy down u. He's still lying flat on the ground. Fine. V, I'm going to move v where his tail is right on top of the tail that u has, so their tails are touching. I'm going to maintain the integrity of v. He's still pointing in the same direction, and he still has the same magnitude, length. Well, now what? Well, can you imagine that these two vectors are adjacent side lengths of a parallelogram? I hope you can see it because I'm going to draw in what the other two sides would look like. Can you guys visualize that parallelogram right there now? I hope you can see it. Well, yeah, so what? Well, the diagonal of this brand new parallelogram is the sum, u plus v. That's the diagonal of the parallelogram. And I hope you see that both of these u plus v's are essentially the same. Which one's better? They're both the same. Which way is better? They're both fine, but I just want to tell you, if you do take a vector calculus class, which comes after this one, and we don't offer it here, you'd have to go to San Diego State and take Math 532, and you see, I think you'd take Math 2D, D as in dog, and that'll be vector calculus. They'll most likely talk about the parallelogram law. That's the most commonly referred to when you're adding vectors together. Just so you know, that's what it looks like visually. Now, what about vector subtraction? What the heck? What if you subtract two vectors? So here's u, here's v. If I translate v so that their tails touch, the vector u minus v is the vector connecting their two tips. Oops, I'm not doing a good job. Okay, that is u minus v. Well, what about v minus u? That's a different animal. Here's u, here's v again. V minus u would also be connecting their tips, but it would be pointing toward the tip of v instead. So this vector here is v minus u. Well, since you guys know that subtraction can be written as adding a negative, I hope you would agree that u minus v is the same as u plus negative v. So if we use the parallelogram law instead, so here's u, negative v would be pointing in the opposite direction. If v is pointing that way, negative v would be pointing, keep the same length, but pointing in that direction. And if we use the parallelogram law, try to imagine these two vectors as adjacent side lengths of a parallelogram, then the diagonal would be u plus negative v. U plus negative v, which is the same as u minus v. So this vector and this vector are the same. They're both pointing a little bit down and to the right, and they have the same magnitude. So u minus v, same as u plus negative v. Okay, and we're done with vector subtraction. Now, what about scalar multiplication? What of it? It's cool because it allows you to stretch or shrink a vector. So let's go back in standard position. Here's the x-axis, here's the y-axis. Suppose you had a vector, I don't know, just any vector here. How about u? There he is. And somebody said, I want you to multiply u with a scalar, rather. What if I said 2u? What does 2u look like? Well, you're doubling u, essentially. So 2u is going to be pointing in the same direction as u, but it'll be twice as long. That's all. Well, what about, oops, no, I don't want to do that. What about like 1/2 u? 1/2 is a scalar. Sure. Well, 1/2 u would simply be a vector pointing in the same direction as the original u, but only half the magnitude. So we shrunk him a little bit. And you can use negative scalars too. What if I said negative 1/2 u? Well, it would be half the magnitude, but pointing in the opposite direction. So it'd be pointing that way, and we'd have negative 1/2 u. So scalars can be positive or negative. Okay. And that is a nice visual on adding, subtracting, and scalar multiplication.